Hello, welcome to MA104 Trigonometry and Analytic Geometry. The first chapter we cover in this class is Chapter 4, which is trig functions. And Section 4.1 is where we will begin with angles and their measure. These are the things that we will accomplish in this section. So if you want to pause here and read through the different things we will do, that will be just fine. We're going to begin with finding the degree measure. And an angle is formed by rotating a ray about its end point. Let's just put these up here. So the initial side is this side here. And then when we rotate this along this arrow here, when we rotate that, we end up at the terminal side. And the angle is also known as the vertex. So we have the initial side, the terminal side, and the vertex are the important things to take from this slide. To find the degree measure, we'll call this the standard position. And the degree measure, we always rotate in this direction. So we will refer to theta as the angle that is formed from going from the initial side to the terminal side. The vertex is typically at the origin, where the initial side is on the x-axis. When we want to find the degree measure, typically we can have positive angles and negative angle measures. The positive angle measure goes from the initial side, or the x-axis, and it rotates in a counterclockwise direction. This will be a positive angle measure. On the other hand, the negative angle measure goes in a clockwise direction, so we will start at the initial side and go in the clockwise direction. That will produce a negative angle measure. A degree is one way to measure an angle, and a full revolution is 360 degrees. So 1 degree is 1/360th of a full rotation. So here is an illustration of a positive angle measure here and a negative angle measure here. So since this is a positive, we will be heading in the counterclockwise direction. A negative angle is in the clockwise direction. We should know from here to here is 180 degrees. So this angle is not quite 180 degrees. So it will terminate before it reaches the x-axis again. Here are some examples. It says sketch the angles in standard position, and we have a 120 degree angle and a -70 degree angle. Before I get started, I want to remind you of the quadrants. This is quadrant 1, and then in a counterclockwise direction, quadrant 2, quadrant 3, and quadrant 4. So remember, we will always start on the initial side, which is the x-axis, where the origin is the vertex. 120 degrees goes in a counterclockwise direction, so it's going to go this way. We should know that this is 90 degrees, so we need to go beyond that. So this angle here is a sketch of 120 degrees. On the other hand, if I have a negative angle, we will start from the initial side, but then we are going to go in the the clockwise position. So here it's not quite 90 degrees, so this here would represent a sketch of an angle of -70 degrees. We will come across complementary angles. You should remember this from your previous math classes, but a complementary angle has the sum of the angle measures is 90 degrees. So if I want to find the complement of a 30-degree angle, I'm going to take 90 degrees minus 30 degrees to get 60 degrees. So that would be the complement of a 30-degree angle. On the other hand, we have supplementary angles. Those sum is 180 degrees. So an example would be if I wanted to find the supplement of a 130-degree angle, I would simply take 180 degrees minus 130 degrees to get 50 degrees. So nothing too terribly complicated there. So we're going to continue with finding degree measure, but now we're going to see something that might be relatively new to you, and it's going to be degrees, minutes, and seconds. So a degree can be divided into 60 equal parts called minutes. So 1 degree is equal to 60 minutes. On the other hand, 1 minute is 1/60th of a degree. And we can break things down even further. A minute is divided into 60 seconds, which it's all very similar to time. So 1 minute is 60 seconds, and 1 degree is 3,600 seconds. Okay. We can take it one step further and say that 1 second is 1/60th of a minute, or 1 second is 1/3600th degree. So what we're going to do is we're going to take these conversions and we are going to convert values that are given to us in degrees, minutes, and seconds, and we're just going to convert them to degrees. So here's our first example. We want to convert this angle measure, which is in degrees and minutes, and we just want that to be in degrees, so some decimal measure. And we know for sure that there are 38 degrees, but this is a part of a degree. So what we want to do is we want to convert this to degrees. So I have 38 degrees plus 12 minutes. And I know that there are 60 minutes in 1 degree. So if I have minutes on the top here, I need minutes on the bottom here in order to cancel those out and leave me with just degrees. So these will cancel. And then I end up with 12 degrees over 60. So this gives me 38 degrees plus 12 divided by 60 is 1/5 or 0.2 degrees. When I add these together, I get 38.2 degrees. And some people prefer to just work with degrees rather than degrees in minutes. This next example comes straight from your text. So all these skill practice problems are directly from your text. Now what I want to do is I want to convert this value here to decimal degrees, just like we did before. So we know that we have 131 degrees. We also know that we have 12 minutes. And just like the previous problem, I want to convert minutes to degrees. And I know that in 1 degree, there are 60 minutes. So this will allow me to cancel out the minutes. I'm going to do the same type of thing with the seconds. I know that there are 33 seconds, and I want to convert these seconds into degrees. So I know that in 1 degree, there are 3,600 seconds, and then these seconds will cancel out as well. So I need to make this conversion and this conversion here. So I keep this 131 degrees plus, this ends up being 12 divided by 60, which again is 0.2 degrees. Over here, in this group, I have 33 divided by 3,600. This is 0.0916 repeating. We've been asked to round to 4 decimal places, so this will become approximately 131.2092 degrees. And this is how you will make these conversions. Now, sometimes we'll want to work backwards. For example, I may be given this here, which is 120.45 degrees, and I will want to be more specific and write this in degrees, minutes, seconds. So really what I need to do is analyze this decimal. I already know that I have 120 degrees, so I can just leave that as is. But I need to figure out how to convert this decimal, or this portion of a degree, into degrees, minutes, seconds. Well, if I want to cancel out degrees, I know that I need degrees in the bottom. And I need to go to minutes next. So in 1 degree, there are 60 minutes. So these degrees will cancel out. Well, it turns out that this multiplies nicely, and this leaves me with 100 degrees and 27 minutes. Now, this next example, the skill practice 2, this one's a little more complicated, and I'll show you why. Same approach as what we just did. We know we have 26 degrees, but I need to figure out how to convert this portion of a degree into minutes and possibly seconds. So I know that in 1 degree, there are 60 minutes. And when I make this conversion, I have 26 degrees plus this here. When I multiply 0.48 times 60, I actually get 28.8 minutes. Well, since this doesn't divide nicely, what I need to do now is take this portion of a minute and convert that to seconds. So now we have 26 degrees plus 28 full minutes plus 0.8 of a minute. And I need to convert this minute to seconds. So I know in 1 minute there are 60 seconds. So these minutes will cancel out, and I can take 0.8 times 60. So I will have 26 degrees plus 28 minutes plus, when I multiply this, I will get 48 seconds. So putting this all together, this converts to 28 degrees, 28 minutes, and 48 seconds. Okay. We're going to move on now to radian measures. And basically, a radian is a measure, it's still an angle measure, but it is different than a degree. And this here kind of explains where a radian comes from. But this angle measure here is equal to 1 radian measure. And page 448 in the text, will kind of explain this to you a little bit better, but the length of the arc here is equal to the radius. So wherever that occurs, that is equal to 1 radian. So 1 radian is simply written as 1, so it really doesn't have any units. This here was explained on the previous slide. Oftentimes we talk about 1 revolution of the unit circle, and 1 revolution of the unit circle is 2 pi radians. So we can think of 1 full revolution as either 360 degrees or 2 pi radians. On the other hand, half a revolution is either pi radians or 180 degrees. So this is pretty important. Sometimes we will want to convert back and forth between radians and degrees, or vice versa. So when we are converting degrees to radians, we will multiply by pi over 180. Since these are the same distance, it's like multiplying by 1, but it allows us to eliminate degrees in this case. On the other hand, if I want to convert from radians to degrees, I will multiply by 180 degrees over pi. And I'll show you an easy way to remember this. Okay, so here we want to convert from degrees to radians. So that means I don't want degrees anymore. So similar to the previous problems, if I don't want degrees, I'm going to multiply something with degrees in the denominator. And I know that I have either pi or 180. So if degrees are in the denominator, I need 180 there and pi here. And remember, with fractions, you can put this over 1 and multiply across the top and across the bottom, and these will cancel. So 120 pi over 180, if you simplify these fractions, the zeros cancel, and these have a 6 in common. 6 goes into 12 2 times, and into 18 3 times. So 120 degrees is the same thing as 2 pi over 3 radians. If you want, you can pause the video and attempt this next one on your own. Again, we want to convert from degrees to radians. So if I want to cancel out degrees, I will put that in the denominator because I need 1 in the top, 1 in the bottom. So those will cancel. This gives me negative 300 pi over 180. When I simplify this fraction, I should end up with negative 5 pi over 3 radians. Let's work in the opposite direction. Now we want to convert from radians to degrees. So now I don't want pi. So if I don't want pi, I'm going to multiply by something with pi in the middle and 180 degrees, pi on the bottom and 180 degrees on the top. So the pi's will cancel. Remember, I can multiply across the top and across the bottom, but I can also cross simplify. Not cross multiply, but cross simplify. 9 goes into 9 once, and 9 goes into 180 20 times. So this is a little bit easier to manage when multiplying. 8 times 20 is 160 degrees. So 8 pi over 9 radians is equivalent to 160 degrees. Remember, radians don't carry any units when they're written. So if you just see a number like negative 1.8, If it doesn't say degrees, assume it is measured in radians. So if you want to pause the video and give this a try, you can. You would simply multiply by 180 degrees over pi. So put this over 1, multiply across the top and across the bottom, and you would get negative 324 degrees over pi. Since this was given to us in decimals, it's assumed that we can go ahead and divide this out and write this as a decimal as well, which would be negative 103.132 degrees. I want to make sure that I use a unit of degrees here when I label this so that this decimal is not to be confused as a radian measure. Now we're going to try to determine coterminal angles. Coterminal angles are two angles in standard position with the same initial side and same terminal side. So here, let me put everything up here. Basically, what this means is angles are coterminal if they have angle measures that differ by either 360 degrees or 2 pi radians. For example, these are known as coterminal angles because 50 degrees, if I add 360 to that, I will get 410. That means these angles are basically the same, because if I were to sketch them, here's the initial side, this angle measure is 50 degrees. But if I go around an additional 360 degrees, I will get to the same terminal side. So these are known as terminal angles. Coterminal angles. Similarly, pi over 6 and negative 11 pi over 6 are the same. So we can either go in the clockwise direction, the counterclockwise direction or the clockwise direction. Remember, if you go in the clockwise direction, it's a negative angle measure. So really, to find coterminal angles, you can either add or subtract 360 degrees, or you can either add or subtract 2 pi radians. That will lead you to coterminal angles. Let's take a look. In this example, it says find a positive angle and a negative angle that is coterminal to this. So for the degrees, what I'm going to do is I'm either going to add 360 degrees or subtract. If I take 110 degrees and I add 360 to it, I will get 470 degrees. Similarly, if I take 110 and subtract 360 degrees, that would give me negative 250 degrees. These are coterminal angles. The exact same thing can be done in part B, but the difference is we are dealing with radians. So I'm either going to add or subtract 2 pi radians. Now it's helpful in cases like this is if you're adding and subtracting and fractions are involved, remember you want a common denominator. So what I can do is notice that I have a denominator of 4. So I need to make this have a denominator of 4. I know that 8 pi divided by 4 is the same thing as 2 pi. So I'm going to add 8 pi over 4. When I'm adding fractions, if the denominator is the same, you keep it the same, and then you will add the values on top. This will give me a 7 pi. So one coterminal angle is 7 pi over 4. We're going to do the same type of thing but now we are going to subtract 2 pi. And 2 pi is the same thing as 8 pi over 4. I keep that common denominator of 4. Negative 1 pi minus 8 pi is a negative 9 pi over 4. So here I have a positive and negative angle that is coterminal to negative pi over 4. You may run across some problems like this. It says find an angle between 0 and 360. Remember, that is 1 full revolution. So we want to find an angle that is between 0 and 360 degrees that is coterminal to 910. So what we're going to do in this case, since this is a positive value, what we're going to do is we are just going to subtract 360 until we have a value between 0 and 360. So if I subtract 360, I end up with 550 degrees. That is not a value between 0 and 360, so I'm going to subtract 360 again. This leads me to an angle measure of 190 degrees, which fulfills our requirement. So 190 degrees is coterminal to 910 degrees. On the other hand, in part B, this is negative, so instead of subtracting 360, in order to get a value in this interval here, I'm going to add 360 degrees. When I add 360 degrees, I get 280 degrees. So 280 degrees is a coterminal angle to negative 80 degrees within the given interval. These are examples of angle measures in degrees. Let's take a look at angle measures in radians. So here, remember, 1 full revolution in radians is 2 pi. So now we want an angle measure between 0 and 2 pi. So if this is positive, I'm going to subtract 2 pi until I have some fraction between 0 and 2 pi. Now I'm going to notice that in part A, my denominator is 6, so I want to rewrite this with a denominator of 6. I know that 12 pi divided by 6 is equivalent to 2 pi. So in this problem, I will take 17 pi over 6 minus 12 pi over 6. When I subtract, I get 5 pi over 6. Again, remember, 2 pi is 12 pi over 6. This value is less than that, so this would be a coterminal angle. If you have a negative, like in part B, we will add 2 pi to this. Notice here that my denominator is 12, so I want to rewrite 2 pi with a denominator of 12. I know that 12 goes into 24 2 times, so I will rewrite 2 pi as 24 pi over 12. So negative 35 pi divided by 12 plus 24 pi divided by 12. When I add these, I get negative 11 pi over 12. Well, this is a problem because I need a positive angle according to the directions. So I need to add 2 pi again. So I'm going to add 24 pi over 12. Now we are in luck. This is 13 pi over 12. And we're good to go. Now we're going to get into some application problems involving arc length, and we will also talk about area and linear and angular speed. Arc length is basically the length of part of a circle. So this here is the arc, an arc, S, and we will want to find the length of that. When we are finding arc length, we use this formula, S equals R, where R is the radius, times theta. One thing you absolutely must know is that theta must be measured in radians. If you are not given the angle measure in radians, then you need to convert it. If you look at our example here, it says find the length of the arc made by an angle of 220 degrees on a circle of radius 9 inches. Well, looking at this, I see that my central angle is measured in degrees. So I need to go ahead and convert this real quick using some information that we learned previously. If I want this to be measured in radians, I need to get rid of degrees. I know there's 180 degrees in pi radians. So the degrees cancel out. And when I convert this, I end up with 11 pi over 9 radians. So applying the formula, S equals R theta. The radius in our case is 9. Theta is 11 pi over 9. Since I'm multiplying, the 9's can cancel, and I'm left with 11 pi. I can multiply these together and find this measure in inches. Since this is a length, it's measured in inches, it'll be approximately 34.6 inches. I kind of liked this example simply because Lincoln, Nebraska is involved. So take a moment, pause this, and read through this problem. So basically what's happening is we have the Earth, and we know that the radius of the Earth is 3,960 miles. And basically, we know that Lincoln is directly north of Dallas. So let's say this is Lincoln and this is Dallas. What we want to do is find this arc length, because if we can find that arc length, we can find the distance between Lincoln and Dallas. So the first thing I want to do, these are just fancy angle measures. So this and this, they're just fancy angle measures. And we know that they are the same distance west. So what we need to do is take the north-south measurements and subtract those. So theta is going to be equal to 40.8 degrees minus 32.8 degrees. This gives us 8 degrees. Well, we know that S is equal to R theta, but theta needs to be measured in radians, and we have degrees. So I'm going to multiply this by pi over 180 degrees. When I simplify this, I get 2 pi over 45, which is approximately 0.1396 radians. So applying the formula, I know that S is equal to R. We know the radius of the Earth is 3,960, and I'm going to multiply it by this value here. And I want to be careful, because if I round this value here, my final answer may be off slightly because of all the rounding throughout the problem. So once you calculate this decimal, you might just want to leave it in your calculator and then quickly multiply by 3,960. And this will give you approximately 553 miles. So I think that's kind of neat to figure out this way that Lincoln and Dallas should be approximately 553 miles apart from one another. Moving on to linear and angular speed. Basically, think of angular speed as a wheel rotating, or think of a pebble in a wheel. And think about how quickly that pebble is rotating around. That is the angular speed. Whereas linear speed is like miles per hour or feet per second. It is linear. It's kind of like a distance traveled in kind of layman's terms. Okay, so we have these different formulas here, and typically we will use this formula and this formula, because if we know the angular speed, we can plug it in and find the linear speed. Just so you know, this is Greek for omega. Okay, let's take a look at a few examples here. Here it says a wheel with a diameter of 1 foot spins at a rate of 40 revolutions per minute. So this is revolutions per minute. We want to do two things here. We want to find the angular speed, and then we want to find the linear speed, or how fast it is traveling in feet per minute. So first, let's find the angular speed. And again, we know that omega is theta divided by time. And really, I'm not going to plug information into this formula, but instead, I'm just going to do some conversions like we've done previously, and it will end up being revolutions per some amount of time, or radians per some amount of time. So take a look at this. We are given that we have 40 revolutions per 1 minute. Now let's think about one revolution. We know that one revolution, so one revolution, one full circle, is 2 pi radians. And I know that theta needs to be measured in radians. So this is 2 pi radians. So one revolution is one full distance around, which is 2 pi radians. Revolutions cancel. When I multiply across the top, across the bottom, I get 80 pi radians in 1 minute. Oftentimes we don't use labels for radians, as mentioned previously, so I can say that the angular speed is 80 pi per minute. And you can see here that this fraction is measured in radians over time, which is omega, or angular speed. And now that we know the angular speed, we can find the linear speed as well by plugging what we know in for omega and applying the radius. Well, we know if there is, let's see here, plugging in the information, we will have 1 foot times what we have over here, 80 pi over 1 minute. And when we convert this, we end up with 80 pi feet per minute, which is a linear measurement. If we want, we can multiply this out to get 251 feet per minute. Here's another example. It says a bicycle wheel rotates 2 revolutions per second. Again, there are 2 parts. We want to find the angular speed and then the linear speed. So if I want to find the angular speed, we want our final answer to take this form. So we are told that there are 2 revolutions per 1 second. And I want to convert this. I need to get rid of revolutions. So in 1 revolution, I know there are 2 pi radians. This will help me cancel out revolutions. multiply across the top and across the bottom, and I get 4 pi radians per 1 second. And you can omit the radian label, oops, if you like. Okay, so here, this one here, let's see, the diameter is 2.2. So if that's the diameter, we will divide by 2 to get a radius of 1.1. And we will multiply this by omega, which we found to be 4 pi. This is in feet. Multiply across the top, across the bottom, and you should get 13.8 feet per second. Okay, moving into the last type of problem. We want to find the area of a sector. So now, instead of finding this length, we want to find the area of this pizza slice, if you will. Again, the angle is measured in radians, and we use this formula here. So, in our first example, we have a circle with a radius of 12 feet, and the area, the angle measure is 135 degrees. So I need to do a quick conversion. I need to convert this to radians. I know that there are pi radians in 180 degrees. When I simplify this, I get 3 pi over 4. Recall from the previous slide that the formula is A equals 1/2 r squared theta. So we have 1/2 times 3 pi over 4. Oops, I'm sorry. That is not the radius. The radius is 12. So 12 squared times theta, which is 3 pi over 4. This is half of 144 times 3 pi over 4. Half of 144 is 72 times 3 pi over 4. 4 goes into 72 18 times, and of course you can plug this into your calculator and get 54 pi, or since it says nearest tenth of a unit, that would be 169.6 square feet. Since we are finding area, we need a label in square units. If you want to practice the next one on your own, go ahead and pause the video and come back. We need to convert 120 degrees to radians. When you convert this, you should multiply it by pi over 180, and this gives you 2 pi over 3 radians. Plugging this in, you have 1/2 times 30 squared times 2 pi over 3. Once this is all simplified, it's 300 pi square feet, which is approximately 942 square feet. That concludes the lesson for section 4.1.